Welcome to Server-Lie, where ideas collide. In a world of tech, come take a ride. Artificial minds with hearts so bright. Join us on this journey, we're taking flight. With every bite, we're here to explore. Unlocking secrets, let's open the door. Server-Lie, let's make the magic flow. From data to dreams, we'll watch it grow. So grab your headphones, come join the fun. In the world of AI, we're never done.
Okay, let's dive into this. There's this analogy I really like. I think it captures the essence of modern AI research here perfectly. Imagine you're, let's say, the world's most sophisticated counterfeiter. A bit nervous, maybe? Your whole goal is printing money, right? But money's so real, it just disappears into circulation. Now, you're not alone. There's this hypervigilant police unit. The financial detective, basically. Their only job is checking every bill you make, and they're constantly getting better at spotting fakes. So because of this constant pressure, this competition, you, the counterfeiter, you have to keep improving, making fakes that are closer and closer to the real thing until, well, eventually they're indistinguishable.
And that simple idea, that sort of competitive adversarial learning, that's the heart of generative adversarial networks. GANs, counterfeiter, that's your generator model.
And the police.
That's the discriminator model, the hypervigilant detective.
So our mission in this deep dive is really to unpack this battle of the bots framework. We want to explain the really deep mathematical challenge in generative modeling that GANs just neatly sidestep. And then crucially, we need to talk about why, even with this elegant theory, they are notoriously tricky and volatile to train in the real world.
Yeah, and for you listening, this is basically a shortcut to understanding the tech behind all sorts of high-quality synthetic stuff, images, deep fakes, even things like 3D models or maybe speech. You'll hopefully walk away understanding how this generator and discriminator play their unique zero-sum game.
Okay, so let's break it down mechanically first. What are the actual pieces? You said GANs have two submodels, usually deep neural networks, right? And they only talk to each other. So first, there's the generator. Its job is creating the fakes, maybe a fake portrait, a 3D model, whatever. It starts with just a random input vector, this noise distribution.
Exactly. So let's pause on that noise distribution. Piezo layer. It's important. Think of it as just, well, a simple high-dimensional cloud of statistical static, random numbers, basically, usually following a standard normal distribution. It's a known, simple starting point. The generator's real magic is learning how to transform their random static into something complex and structured, something that looks real, like a photo. It learns this incredibly complex mapping.
Okay, got it. Random static in, potential masterpiece out. And the second piece?
That's the discriminator, D. It takes any sample, could be real data, could be a fake from the generator, and it outputs just one number, DDXX, a probability between 0 and 1.
Representing
its best guess on the probability that the sample it's looking at is real. It's fundamentally just a standard binary classification task, real or fake.
And this is where the competition kicks in, right? Because their goals are completely opposite.
Precisely. The generator is always trying to make the discriminator perform worse. It wants to fool D. Its success is D's failure.
While the discriminator is trying to get better and better at spotting the fakes.
Exactly. It's a true zero-sum game. The generator wants to maximize the chance D makes a mistake. If D correctly identifies a fake, well, the generator immediately gets feedback to update its parameters to make a better fake next time.
And if the generator does fool the discriminator, if D thinks a fake is real,
then the discriminator has to update his parameters to become, well, less gullible, more discerning.
And this just goes back and forth.
Back and forth, iterating until the generator becomes a master forger, creating samples that are often so good, even humans struggle to tell the difference.
Okay, but to really grasp why this whole competitive setup is so clever, we need to understand the problem it solved, right? What was the big challenge before GANs?
Exactly. Before GANs came along, the main goal in generative modeling was trying to directly estimate or approximate the true underlying data distribution. We call it $10. Think of $10, like the perfect ideal process that generated all the real data samples we actually see. It's a ground truth distribution we're trying to mimic.
And this is where things get mathematically sticky for the older methods, especially things based on maximum likelihood.
Very sticky. If you want your neural network's output, let's call it PX2, to be a proper probability distribution, it needs two things. First, non-negative outputs, usually easy.
Okay.
Second, it has to be normalized, meaning if you integrate that function over the entire possible data space, all possible images, say the result must equal 1.
That sounds complicated to ensure.
It's worse than complicated. Often, that integral doesn't naturally equal 1. It equals some other value, let's call it z, the normalization constant, or partition function. So you have to divide your output by z to make it a proper probability.
Right.
And here's the killer problem. In deep learning, especially with high-dimensional data like images, this z is almost always intractable. You can't calculate it precisely. You can't even estimate it accurately without crippling computational cost.
Intractable. So you can't actually compute the true probability px dollar.
Exactly. Which means when you're training your model, you don't know if you're actually making px higher or if you're just accidentally inflating z even more. You're kind of optimizing blind, without a clear lock on the true probability. It's a massive roadblock.
Ah, okay. So how do GANs dodge this?
This is the genius part. GANs completely sidestep the whole z problem. They reframe the goal. Instead of trying to explicitly learn dollars and then worrying about dividing by z, the generator implicitly learns the target distribution. It does this by learning that mapping we talked about from the simple, known, already normalized latent distribution PZZ, the static, onto the complex target distribution of dollars in the data space.
So the generator learns to map random noise to points that look like they came from the real data distribution.
Precisely. Its job is just to make sure its output, GZ, produces points so convincing that the discriminator can't tell them apart from the real dollar samples. The comparison is done by D. No need to ever compute Z.
It's elegant. Just bypass the impossible calculation by setting up this game instead. Okay, let's dig into the math that makes this game work. What actually guides this process toward, ideally, perfect generation?
Well, what's really neat is that the foundation is something pretty familiar in machine learning, the discriminator's loss function. It's basically built on the standard binary cross-entropy loss.
Because it's just doing classification, real versus fake.
Right, that loss function works perfectly for its job.
But their goals conflict. So how is the whole thing structured? You mentioned game theory.
Yes, the entire process is formalized as a minimax game. Think of a value function, v. The generator tries to minimize v. It wants to minimize the detectability of its fakes, minimizing the distance to reality. Meanwhile, the discriminator tries to maximize that same value function v. It wants to maximize its ability to correctly spot the difference. They have perfectly opposing goals on this single value function.
Minimax. Okay. And training the GAN is like trying to find the stable point in this game.
That's the idea. Mathematically, training a GAN is equivalent to searching for a Nash equilibrium. That's the point where neither the generator nor the discriminator can unilaterally change its strategy, its parameters, and approve its own outcome.
So the counterfeiter is making fakes that are exactly as good as the police's ability to detect them, and neither side can get an edge. That standoff point.
That's a perfect way to put it, the perfect standoff. And there's a really profound theoretical guarantee that comes out of this framework. If you assume you've reached this Nash equilibrium and critically assume the discriminator is optimal at its job, then minimizing the generator's loss turns out to be mathematically equivalent to minimizing something called the Jensen-Shannon divergence, the JSD.
The JSD between what?
Between the true data distribution, $,
Yeah.
and the distribution the generator is producing, PG job.
And why is minimizing that divergence so important?
Because the JSD has a key property. It's always non-negative, and it hits its absolute minimum value of 0 only when the two distributions are identical, when PP equals PG day. This is the beautiful theoretical proof. It's the mathematical justification that says if your GAN training converges perfectly to this ideal state, the generator will produce data that perfectly matches the real data.
Okay, that's the elegant theory, a system guaranteed to work in theory. But now the messy reality. Why is actually training these things known to be so difficult and, well, unstable? You mentioned the optimal discriminator is key to the theory.
Right, and here's the big paradox, the paradox of optimality. In theory, you need that optimal discriminator to provide the perfect guidance for the generator. But in practice, as the discriminator gets really, really good, close to optimal, easily spotting all fakes, the feedback it sends back to the generator, well, the gradients, they start to vanish.
Vanishing gradients.
Yes.
So the better the discriminator gets, the less information it actually provides.
Exactly. If the police are 100% sure a bill is fake, The error signal they send back is effectively zero. There's no nuance, no you were close here but wrong there. It's just fail.
Yeah.
And since the generator learns entirely based on the discriminator's feedback, if that feedback vanishes, the generator stops learning. Training stalls completely. The very condition needed for theoretical convergence prevents practical learning.
Wow, okay. That's a fundamental tension right there.
It really is. It's a major headache for anyone trying to build these things.
And what about the other way around? What if the generator gets too good too fast?
That leads to the lousy discriminator problem. If the generator updates too quickly and starts making really good fakes early on, the discriminator can fall behind. It gets overwhelmed, confused.
How?
And if the discriminator is confused, the gradients it sends back become noisy and unreliable. It's like the police unit is just guessing randomly.
Yeah.
The counterfeiter doesn't get any useful feedback and might just start producing junk. The whole system can diverge or collapse.
So it's this constant balancing act. You need the discriminator to be good, but not too good.
Precisely. It's why you hear about developers doing things like training the discriminator for, say, K steps for every one step the generator takes, or giving the discriminator a higher learning rate.
They're essentially trying to carefully regulate the learning speed of both players, like constantly babysitting the process.
A lot of the time, yes. It requires careful tuning and monitoring to keep them in that productive zone. D needs to be just bad enough to provide useful gradients, but good enough to actually push G forward. And on top of that, there's the fundamental issue that not all minimax games even have a nice, stable convergence point.
What do you mean?
Well, as this classic example, imagine two players controlling parameters x and y. One tries to optimize the function 6y dollars, the other tries to optimize xy dollars. There's an equilibrium point at 6y dollars, but if you train them by alternating optimization, one player updates than the other, then the parameters can end up just tracing a circle around the equilibrium point forever. They never actually settle down, they just orbit.
They get stuck circling the drain, never reaching the goal.
Kinda, yeah. Stable orbits instead of convergence. It shows that the game dynamics themselves can prevent reaching the desired state.
Okay, and then there's the most infamous problem, right? The one everyone talks about with GANs, mode collapse.
Mode collapse, yes. This is where the generator gets, well, lazy. Or maybe clever, depending on your perspective. It finds a loophole. It figures out that it can consistently fool the discriminator by mapping almost all the input noise vectors, all that random static, to just one single, highly realistic output, or maybe a very small number of outputs.
So instead of generating a wide variety of realistic images, it just keeps producing the same perfect-looking one over and over.
Exactly. Maybe it finds one image of a cat that the discriminator thinks is real. So it just keeps generating that exact same cat, regardless of the input noise.
It succeeds in fooling the discriminator because the cat is realistic.
Right. It gets an A+ on realism for that one mode, but it completely fails at the overall goal, which is to capture the full diversity, all the modes of the real data distributions.
Yeah.
You wanted pictures of all kinds of cats, and you just got thousands of copies of one specific calico.
That's mode collapse. It found one good answer and just stuck to it.
That's it. It's probably the most notorious failure mode.
Okay, so despite all these training challenges, the vanishing gradients, the potential instability, mode collapse, when GANs do work, they achieve pretty incredible things, don't they?
Absolutely. The results can be stunning. High-quality synthetic data generation is the obvious one. Fake faces, generating realistic textures, 3D models, even things like synthetic medical images or chemical structures.
You also mentioned video frame prediction. How does that work?
Yeah, that's a fascinating application. The generator tries to predict the very next frame in a video sequence. The discriminator's job is to look at the predicted frame and judge if it looks like a natural continuation of the video, or if it looks artificial, maybe blurry or jerky.
And why is the GAN structure good for that?
Well, traditional methods for prediction often use loss functions like mean squared error. These tend to average possibilities, leading to blurry predictions, because blurring minimizes the average error. But the GAN's discriminator forces the generator to produce sharp, high-frequency details. It demands realism and temporal coherence. That's why GANs are great for things like predicting the immediate future in, say, autonomous driving simulations, or even enhancing surveillance footage.
And image enhancement, too, like super resolution.
Right. Taking a low-resolution image and generating a high-resolution version. The generator essentially has to hallucinate the fine details, guided by the discriminator, which knows what real high-res images look like.
And even non-visual stuff, like encryption.
Yeah, it's been applied there, too. You can frame encryption as a game. One network tries to encrypt data securely, while another network, the adversary, tries to break the encryption. This competitive process can lead to discovering quite robust encryption methods.
So naturally, people have developed ways to try and fight back against the training problems, like mode collapse.
Oh, definitely. There's been a ton of research into stabilizing GAN training. One technique is mini-batch discrimination.
How does that help with mode collapse?
It gives the discriminator a little extra information. Instead of judging each sample in isolation, it gets to see features from all the samples in the current mini-batch. So if the generator is trying to collapse and produce the same output repeatedly within that batch, the discriminator can easily spot it and say, hang on, these are all suspiciously similar. It forces the generator to maintain diversity within the batch.
Makes sense. And you also hear a lot about Wasserstein GANs, WGNs.
Yes, WGNs were a major step. They fundamentally changed the underlying mathematics. Instead of binary cross-entropy and minimizing JSD, they used a different metric called the Earth mover's distance, or Wasserstein distance. The key benefit is that this distance metric provides smoother, more reliable gradients, even when the discriminator is performing very well. It directly tackles that vanishing gradient or paradox of optimality problem we talked about, leading to much more stable training in many cases.
Okay, so wrapping this up, generative adversarial networks, GANs, they're built on this really elegant adversarial idea. Two models locked in a zero-sum game. And this competition cleverly sidesteps major mathematical hurdles in traditional generative modeling, allowing them to produce incredibly realistic synthetic data by implicitly minimizing this deep mathematical divergence, the JSD.
Good. As we've seen, the reality of training isn't quite so clean. That inherent competition, this sort of internal AI arms race, creates its own set of complex challenges, vanishing gradients, instability, the dreaded mode collapse.
Which leads to a final thought, perhaps.
Yeah, I think it raises a really important question for the future of generative AI. We know this competitive adversarial approach is incredibly powerful for achieving high fidelity. But we also know it brings instability. So the question is, how do we design the next generation of these systems to keep the power of that competition, but somehow engineer in the stability needed for reliable, guaranteed convergence? How do we get the best of both worlds?